Symmetry, counting symmetries. This will be a rather short lecture. I just want to make a few more points about counting the symmetries of an object. So suppose I have a rosette or maybe some other kind of a figure, and I'm wondering what symmetries does it have? Or maybe I just want to answer the question, how many symmetries does it have? Now, to answer that question, first we all need to agree about when two symmetries are considered to be the same. So rather than a rosette, let me take a circle. And again, to keep track of what I'm going to do to a circle, I'm going to draw something inside of it. I'm going to imagine that circle as the boundary of a quarter, as shown here. So let's think about starting with the quarter sitting on the table in front of us. Suppose that we have George Washington facing straight up, looking off to the left. Now, one thing I could do to the circle, and therefore to the entire quarter, is to rotate it clockwise by 70 degrees. So that would be as if we were letting George lean backward in his chair. In fact, we're going to let him lean back quite a bit. We're going to rotate by 70 degrees clockwise so that he's looking way up in the sky. Now, we could also rotate clockwise by 430 degrees. Now, 430 degrees is quite a bit. In fact, if you're going to rotate something by 430 degrees, you need to rotate it more than a full turn, right? You're going to rotate George around, not just lean him back in his chair, but continue to turn him till he's back to his original position, and then keep going. And how much more? Well, an additional 70 degrees. Now, as soon as you've realized it's a full turn of 360 plus an additional 70 degrees, you'll realize that the final position you achieve will be the same as if you had done the smaller rotation by 70 degrees. What that means is every point of the circle and every point of the quarter has been moved to the same position by the larger rotation as by the smaller rotation. They have exactly the same effect on every point. And for that reason, we consider those to be the same motion. That is to say, the same symmetry of the circle. If we're counting symmetries, we wouldn't want to count those two twice. Now, once you realize that, you'll also realize, well, there's another way to get George to that final position. Rather than to rotate clockwise by some amount, I could rotate him counterclockwise by an appropriate amount. So if I want to get him from the initial position to this position where he's leaned backwards looking way up, instead of leaning him backwards, I could actually ask him to do a somersault forward. I could ask him to rotate counterclockwise by 290 degrees, and that would take him to the same position. Now, how do I know it's 290 degrees? Well, simply because 290 degrees plus 70 degrees will give us back 360 degrees. Again, those two motions are considered to be the same. If we're thinking them as symmetries of the circle, they are the same. So in fact, all three that I'm showing you there are the same symmetry. They aren't three different symmetries. And in general, if we have an object and we consider two different motions, and we discover that those two motions have the same effect upon every point, then we're going to consider them to be the same motion, not two different motions. So when we came to the five-pointed star and we're asking what symmetries it had, I gave a rather short list. I said we could rotate by 72 degrees clockwise, or 144 degrees, or 216 degrees, or 288 degrees. But I didn't mention rotating it by 432 degrees, and I wouldn't do that because that's just the same as rotating it by 72 degrees, right? I wouldn't want to say that again. That would be repetitive. So when I'm naming rotational symmetries and saying clockwise, the only angles I would want to mention would be 72, 144, 216, and 288. We also saw, of course, that there were reflection symmetries, so there are 5 axes of symmetry. So it seems, again, that we have this complete list of 9, but of course, remember, there's one other thing that we always want to count, and that is doing nothing. Mathematicians call this the identity motion, or simply the identity. This would explain, by the way, why we don't count rotation by 360 degrees. Often students want to say, oh, well, rotating by 360 degrees is a symmetry of this object. And of course they are right, but that's not the canonical way that we list that symmetry because it's equivalent to doing nothing. So we count it when we count the identity. Notice, by the way, with this convention, every object has at least one symmetry. But if that's its only symmetry, we'll continue to say that the object is asymmetric. Now to finish up here, let me do a little probability problem. When I return my DVDs to Netflix, I first of all have to stick the disc inside a small square envelope, and then I have to take that envelope and put it in a bigger envelope, as is shown here. So you're looking at the outer envelope, and just through that little opening, you're seeing the barcode. Well, that meant I was actually successful in doing what Netflix would like me to do. I've stuck the inner envelope, the square envelope, inside the big envelope so that the barcode was visible. But it's very easy, if I'm careless, actually to do this incorrectly. In other words, to take the inner envelope, which is a square, and shove it in the big envelope so that the barcode isn't showing. In fact, here's the problem that I want to ask. Suppose I take this inner envelope, which is a square, and I just carelessly, at random, put it inside the inner envelope. What's the probability that I did it correctly? Well, this is really a question about symmetries. What I'm really asking is how many different ways can I put the square into the inner envelope? What are the symmetries of a square? And how many symmetries does it have? Well, the square is an example of a dihedral rosette with n equals 4. That means that it has 8 symmetries. We will actually think a lot more about these symmetries in the remainder of this unit, but there are indeed 8. That means that if I just carelessly put the inner envelope into the outer envelope, there's only one chance in 8 that I did it correctly. And so the answer to the problem is 12.5%.